Hung is a graduate of the Oregon State University, where he studied under the supervision of Cora Bordale, who was a student here, as some of us might remember, and currently a professor at UMass Amherst, and doing what I think is just wonderful, groundbreaking work in algorithms. He was telling me about some of the techniques that he's going to discuss today, although he won't maybe get into as much detail. And it just really helped me to see graphs in a way, in a new way. And I've really enjoyed his contributions up to now, and I continue to expect great things. Good. Thanks for coming.
Right. Yeah, thanks, Phil. That's a very nice introduction. So, yeah, it's good to be here. Like, first time giving a talk here. Like, my advisor was Brown student, so I always wanted to come here and give a talk. All right. So yes, my name is Hang Lee, and I try not to be too technical. So if you expect deep proof or anything like that, you probably would be disappointed. I try to be a little bit more high level, philosophical maybe, but without even like I don't like to be philosophical. But anyway, so in this talk I'm gonna introduce new kind of decomposition of planar graph, and mention some applications, and hopefully everyone gonna take something out of this talk. Might not be the technical detail, but what happened? Do I press the wrong button or something?
I think your computer just went to sleep.
Maybe. All right. Oh, it's up. No. The computer is up, but not on the projector.
Oh, here. Wait.
All right, good. All right. Sorry about the hiccup. Right. So this talk is very much I work with 6 other people that I've been working with over the last few years. So Xianqi Zhang is at Dartmouth. Jonathan is a student of Xianqi at Dartmouth. Arnold Fuser from Byland University in Israel. Lazar is a student of Shai Solomon. Both of them at Tel Aviv, and Kwang is my PhD student. So, because the title of this talk is a planar graph, so I think that I should tell you what it is, which is a graph that you can draw on the Euclidean plane without S-crossing. Right? So the left-hand side here, the way it's drawn might not look planar in any sense because you have a lot of crossing here and there, but actually you can find a different drawing that have no S-crossing. But if you look at the graph at the bottom, is K phi here, and there's no way you can draw it without S-crossing, which basically is obtained by the graph upper here connecting 1 and phi. And you can see in this figure, if you connect 1 and phi, it had to cross somewhere. Right? So this is the graph that we'll work with here in this talk. And why planar graph? If I'm giving a job talk, here's I'm going to say, there's applications in routing and road network. Like Phil's been working a lot with road network and things like that. But this is not a job talk, so I'll pass up on it. But personally, I work on planar graph because of over the years, people discover many interesting algorithmic ideas in that, and that really draw me to planar graph because you can you can discover this beautiful idea, and that is my personal reason why I work on planar graph. All right, the starting point of this talk is a paper by Phil and Falk-Epstein and Still 5 years ago, probably more than that, but which is about embedding a planar graph into low tree width graph. Okay, I'll tell you what it is. But that's the starting point of this talk 5 years ago. So what this paper is doing is that if you take a planar graph with some bound diameter, let's say delta, and you to any epsilon constant of the choice, think about epsilon is 0.1. And what he said is that you can map this to another graph like H that almost look like a tree. Okay. So we're going to go graph with low tree width. I wouldn't give the definition of tree width now, but a good thing to keep in mind that it very much look like tree. Up to structure is almost look like tree. Okay, very similar to tree. so that the additive distortion is only epsilon times delta, where delta is diameter. And what do I mean by additive distortion at most plus epsilon delta? What I mean is that if you look at the distance of u and v in this new graph compared to the distance between u and v in the input graph, it's not differ by more than epsilon delta. So it's always at least a distance in the original graph, but it's not more than by an epsilon delta amount, where epsilon is any constant of the choice.
So this is for all UV, right?
For all UV, that's good, right. And think about epsilon as constant. So what he said is that you can embed the graph, which could look very complicated, into a graph with tree with constant, meaning that it's very close to being a tree with very little distortion in the distance. So, even though this polynomial is 1 over epsilon to the 58, I made that up, probably even higher.
Yeah, it's probably higher.
Right, probably higher, but it is some big constant, right? Right. Yeah, but what's amazing about this, if you look at these conceptual message of this result is saying that you can embed a planar graph into some graph that almost look like tree with very little distance distortion. So that to me is very surprising, because you can do something like this. And so I look at the paper. So back then I was looking, wow, this is amazing. Let's read the paper. After 1 hour, I get some understanding, but still not a good understanding of the paper. But then I give it another day. Still get something more. I understand a little bit more, but still not to the point I understand the paper fully.
I would have expected this to be less and less understanding as you read it.
But after a week, it's still, I can understand a little bit more, but still not the full picture. It's still like a big mess to me. But this is how much, this is how much I can get out of a week. But after a month, I had an idea, which is, let's go back to the basic. try to think about problem from ground up. Okay, so we know that something great exists, right? So let's think about, whether we can have a simple proof or something like that. Great results should have simple proof. And so when I go back to the basic, there's a very beautiful paper by David Eisenstadt and Clyde and Matthew in sort of 14 saying that you can do this embedding, but the tree width depends on the number of vertices of the input graph. It gets larger when the graph is larger, but not too bad. The dependency was log n, which is not too bad, but still not great, but not too bad. And the dependency on epsilon is just 1 over epsilon. So it's log n over epsilon tree width, and the embedding is very simple. Okay, though I wouldn't be able to describe here. Modular, some standard background in planar graph, then the embedding is quite simple. And so the question we ask is, can we even beat the log n? Get anything better than log n? That would be a win. So that's the question that I sort of trying to do back then. And yes, we did. After probably 3 years, we get something better, which is log n squared, which is a very weird number. I'll tell you why. We have this weird number. But we get something like log n squared over epsilon. So it can beat log n, but still, the tree width is going to grow if the input graph is larger. So it's still not a constant number. But it beat log n. So that is, at least for this question, we can do that. And let me tell you a little bit about what's going on. I mean, I'm not trying to give you the full proof. It's just a key idea in the proof, so that maybe you can take out something from this. Which is, it turns out that to be able to do this, we only need to look at what we call tree shortcutting, a shortcutting problem on tree. Okay, what is the problem? Let's say that I give you a tree. Okay, a tree here, some of these vertices. The tree could be S-weighted. But for now, the thing about it is unweighted. Okay. I want to add some new edges to the tree. I mean, here I only add 1 edge. So probably not interesting. In general, you can imagine you had a very big binary tree, and then, or even not a binary tree, a very big tree, and then you can have to add a lot more edges. But the idea is that I want to add some edges Does it satisfy two things? The first is that I want the new graph to still look very much like tree. Okay, it has more tree width, meaning that I don't want to add a lot of edges so that it looks crazy. I want the new graph still look very much like tree. And I want for every U and V, if you look at shortest path from the new graph, that I allow them to use the new edges that I added. This shortest path for every pair of the vertices only have a few edges. So that are two things that I'm looking for. Right? If you think about, if you start with a complete binary tree, then every shortest path have length probably at most log n edges. But here I want a lot less than log n edges by adding some new edges. But at the same time, I want the new graph after I add edges to still look like tree. And so that's the problem. Right. And we thought about it for some time, and it turned out that we find a sweet spot where I can do something interesting. And you can see the tree width versus top trade-off here, because I want to add more edges to reduce the number of edges in the shortest path, but at the same time, adding more edges makes the graph less look like tree. Right, so there's some sort of inherent trade-off here, and our goal is to find some spot where the tree width is more and the hop is small. Right, you have to find some right kind of trade-off, and that is what we ended up with, which is somehow you can find the set of edges that you add, so that the tree width is log n. Okay, still very much like tree. And you can get from U to V going through only log n number of edges. Like I said, if you start with a complete binary tree, then every path have some path between two leaves gonna probably have log n. But now I add some more edges, I reduce the number of hops exponentially from log n to log n, and then the tree width is also blown up, but not a lot. And that's the sweet spot that we found out. And together give us an embedding with tree width log n squared. Basically, it is a product of the tree width time hop here. Okay. So if you start with a binary tree, the tree width is 1 because it's a tree. Then the hop is log n, but you put it here, you just get log n over epsilon. Here somehow we find a sweet spot between the tree width blown up and the number of hop, and that turned out to be tight. We can show that that's the best you can do. But not in the paper. Back then we didn't know how to show it tight, but now we know that it is the best you can really do.
So do you have a lemma that for any such construction you will get an embedding whose quality is a product of the
Yep. So there is a black box lemma saying that once you get, you can get embedding with the product of tree width and hop.
Is that something that you're going to tell us about?
I wouldn't tell you. That, unfortunately, I wouldn't be able to tell you. But that is one thing that I think a key takeaway message from my paper. If you ask me, like, okay, modulo, that if I know everything about planar graph, what would be the key takeaway? I would say this. Okay. All right. So that's great. We beat log n, but still unsatisfying, because these results say nothing about planar graph. It doesn't change the way people think about planar graph. We don't prove any new structural result. We don't prove anything new. We had a nice technique, we had a nice trick, and we had a nice result, but it's not satisfying because it doesn't tell you anything about planar graph. And so we had to move on, but we also did not have any new idea. Since we did this result, at least I don't know how to do it better.
As far as like the impossibility result is concerned, if I allow myself, say, like Steiner nodes, but still restrict myself to a small tree width, is it either sufficient for your purposes, or I guess on the flip, is the impossibility result?
That are a good question. Steiner nodes is not sufficient for my purposes, so I'm not allowed to have Steiner nodes.
So the impossibility result is on, just to be clear, is not on the embedding, it's on the other result.
Yeah, it's on these shortcutting, like this impossibility.
That was probably clear to you, but maybe not to everybody. So.
Right.
As in, you cannot have a tree shortcutting construction whose product is lower than
log n squared. Yeah. So we prove about the log n squared is the best you can do if you look at the product of the tree with the hop, the hop bound.
Sorry, what do you mean by this does not imply anything? I thought there's something that you're not telling us, which says you can get embedding with.
Right.
But this embedding here is a planar graph result.
This one is a planar graph.
Yes.
Okay, then this one is a really different problem. It's nothing to do with planar graph. But then it's turned out that in the proof of this, we reduce this problem.
Right.
So
That I get.
right.
But if you go to the next slide, there's a red sentence I didn't get. Like, what do you mean?
Oh, right. So what I mean is that we do this thing,
Yeah.
but it has nothing to do with planar graph.
Okay.
And the proof from here to here is a standard technique.
Okay.
It doesn't give you sort of like, it doesn't tell you what would be something new, right? It's all the sort of idea we reduce from here to there, all using existing technique that people are familiar with. So it really doesn't tell you anything new if you know the basic of planar graph.
So the theorem says there exists an embedding for a tree
No, I was embedding like a planar graph.
of a planar.
Right, of a planar graph of diameter delta into graph with tree with this amount.
Planar graph is n nodes.
Right, that's true, the planar graph, yeah. I ignore this planar graph because in the previous talk, I was trying to say that what Phil got, or maybe it's a bit bad idea to go back because it's very long. But anyway, this is the full theorem, but I try to take out some of these things. But that's what Phil got with his student is a constant. Even though the constant might not be a small number, but it's still a constant. It doesn't grow with the number of vertices. All right. So at least we succeed with the question of beating the log n, but it still doesn't. It's not satisfying. And I did not have any new idea since then. Meanwhile, we're looking at a different problem, which is this problem I picked up when I was at an ISERM workshop in May 2019. Like often everyone gave the talk, I still remember. Which is a tree cover problem. So let me take a moment to define what it is. It's a completely different problem. You see, now suppose that I give you a planar graph, G, okay? I want to construct a collection of trees. I want a small number of trees. I don't want, like a large number of trees. I want a small number of trees, just a few trees, so that, the number of trees is small. And then if you look at any two vertices, like in Y of your choice, look at any two vertices, there exists some tree in the collection, maybe this tree here, the middle tree here, where the distance in the tree is not bigger than distance in the original graph by more than 1 plus epsilon factor for any epsilon of your choice. Okay, think about epsilon 0.1. So basically, I want a small number of trees so that for every pair point, there is some tree in the collection that preserve my distance. So that's the problem. Okay, any question about the problem? Because I don't want to lose you on.
The trees can overlap edges.
Yeah, it can reuse vertices again, it can reuse edges again as long as it has small number of trees. So what I'm looking for is really small number of trees. Because you can do it with n tree by doing single shortest path tree from every vertex. Right? But n tree is not, it's too big. Here I want very small tree. And in the talk, like I said, I attended the talk by Nerman in the ISERM workshop in the 19. They show how to get a cover. What I meant by the cover is a collection of tree. So I call the collection of tree a tree cover. Okay. And they managed to get a cover with log n squared over epsilon. So in planar graph, the log n come up a lot because of the standard technique, give you a log n squared. But they get small number of trees, which is polylog, right? Which is also, an interesting result as itself, but applying standard technique in planar graph. And what the question is that they want to get a constant tree for any constant epsilon. Okay, for example, if you give me epsilon equal to 0.1, I get 100 trees for every graph, for every planar graph. I don't want the number of trees grow with the number of vertices of the graph. So that's the problem. Is it clear? So that's a problem that we set out to try to understand. Like, can we do it? And so, after a long time, probably, we came up with some sort of reduction. We're not solving this problem, but at least we came up with some sort of reduction. Allow you to say that, well, it's a fight to do tree cover, to construct tree cover for a graph with small diameter. That is the basic merit of the reduction, saying that, oh, it suffices to just look at graph with small diameter. Here's formally what the reduction is saying is that if you start with a planar graph of diameter delta, and if you can construct a tree cover for the graph with diameter with additive distortion epsilon delta, by additive distortion now still the same as tree width embedding, like the distance in some tree is not more than the distance, original distance in the graph by an epsilon delta amount. Right? If you start with a planar graph with diameter delta and you can construct me a tree with small additive distortion and small psi, then I can give you a tree cover with multiplicative distortion 1 plus epsilon and the psi, which is roughly the same. The tilde here is log 1 over epsilon loss. So it doesn't depend, the loss doesn't depend on the number of vertices. So that's what it said. Like, so what the result is trying to say was that it suffices to look at planar graph of small diameter.
Does the little tau there for the size, is that the number of trees?
So the number of trees, right? The size is always the number of trees.
Yeah.
Great questions. Okay, so this result is basically a reduction to allow you to say, well, let's focus on graph with small diameter. And if you think about additive distortion, it's really easier in some sense. Because if you think about like delta here is the diameter of the graph, and you look at epsilon delta distortion, what it means is that for every closed pair x and y, for example, if their distance is very tiny, let's say 1, where delta is say a zillion, then I can afford to play, 1% with a zillion, probably. Like, so it's a big number. So for very close pair, really is additive distortion saying that I could tolerate a very big distance, a very big distortion. That give me more wiggle room. And of course, for a pair that are very far, like almost the diameter, then the additive distortion is roughly the multiplicative distortion. Right. So what it says is that, for small distances, I can afford a large distortion, and that gives me some wiggle room. And so that's why, additive distortion is easier. But construct this thing is a different problem. Like it's more challenging. But is it really easier, right? Using standard technique of planar graph, get you log n over epsilon, number of tree, which in turn give you log n over epsilon for the multiplicative distortion. Is this an improvement over the result that I mentioned before? But it's still not a constant. I'm looking for constant. And I want to do like constant for any constant epsilon. Something like, 1 over epsilon to the power 4 or 5. And let's call the tree cover with additive distortion the additive tree cover. Now you can see that the embedding result, we also look at additive distortion. Tree cover, we also look at additive distortion. So but that is as close as they can get. The two problems is very, very different from each other. All right, and now I can tell you about what new. Unfortunately, proving this thing is technical, so I wouldn't give you the proof. But it's in my opinion, it's a new understanding of planar graph that allow us to get other results. And so I'm excited about this new structure. So what is this shortcut partition? So let me give you an idealized version, which is clean. But in reality, we don't know how to get this idealized. I'll tell you what the reality is. But the basic idea of the idealized version is also quite simple. So let's say that I give you a planar graph of diameter delta. I just want to partition into a bunch of clusters. Looks something like this. And each cluster must have a size epsilon delta. Okay, I just want to partition the graph into cluster of small diameter, epsilon delta for any epsilon of your choice. So that's the first criteria that I'm looking for. For my clustering, the second criteria is probably the most important, and that makes this partition interesting, because if I don't look at the second criteria, then you can just do it greedily. Why not just construct a cluster and then remove it and then construct another one, right? So the second criteria is saying that if I look at any shortest path between any two vertices x and y, I want the shortest path just going through few clusters. Okay, I don't want the shortest path take a long detour to all of these things and get to y. So I want to say that the shortest path only hop through a few clusters. This is order 1 of epsilon cluster. Think about epsilon constant, then I want my shortest path only going through a constant. In this case, my shortest path going to 1, 2, 3, 4. Right? You can think about the graph could be larger and larger, infinitely larger, but the number of clusters that pass through my shortest path is just, say, 10. That's the idealized version. And actually, this idealized version has a name. It's called scattering partition. But this is not something we could get. But because, this is the ideal planar graph that look very much like a grid, and it look nice, but in reality, planar graph could look very nasty. And so that makes this constructing this thing difficult, and it's still an open problem whether we can do that. The reality is here's what we do, I'll take my time to explain what it is, but if you feel like it is complicated, then, it is what it is. But, the ideal version, we don't know how to do it, but actually we can get something very close. It's just a statement, it's a bit strange. So we still want to partition into cluster. Okay, thing like this. And then for every 2 vertices, I want to show that there exists a 1 plus epsilon approximate path. No, I don't care about the exact shortest path anymore. I care, I show that I want a good approximation of the shortest path. So that these approximations is only going through a few clusters. Okay, so what I'm saying is that I want a partition where if I look at every 2 pair vertices, there is an approximate path that goes through few clusters. That's what I want to do. That is what we can do. Okay, but that is actually how the statement look like. But for now, for this talk, let's go with the idealized version.
Sorry, can you go? What does contain cluster? Only contains cluster.
Right. So this is the approximate path. Think about the green here.
Sure.
And then I want this path and another path in the cluster graph. I think about I take a cluster, I contract into a single vertex, and then I get a cluster graph. I want to say that there is another short path going from H to Y in the cluster graph. Okay, so in this particular example, another short path going H from C2, and C2 go directly to C5.
I see. Okay.
So I want an approximate path where it's passed through a few clusters. That's an intuitive way to think about it, even though this statement is much messier than what I meant to say.
Sorry, so I just want to be sure. So pi tilde goes through a bunch of clusters, right?
Yeah.
And you're saying, I don't know.
There is another path.
Yeah, this pi reverse path is only containing
a few hop, and is only allowed to contain clusters that are intersected by the approximate path. So think of a path that could pass through many clusters. I allow the approximate path to go as long as I can find a path that going only through the cluster intersect by
use all of them, but
right.
You can only use the things
as few of them as possible.
And the shortest path, or nearly shortest, approximate shortest path, pi tilde, can enter and leave a cluster more than once.
Yeah.
Right?
It can enter and leave cluster more than one.
Yeah.
Yeah.
Okay.
So I need to, good.
Yeah, just clarify the last point. So, for example, for the blue line that you drew here, would this be considered just 3 clusters? Approximation.
So this blue line is an approximation that could go still through a lot of clusters.
Yes.
But as long as I can find a short cluster in the cluster graph that going past through P tilde.
Would it be right to say that it will be disconnected then, like the distance between x and y?
It's not disconnected because I want to say that, if you look at this blue path, it goes through a lot of clusters.
It actually goes through all the clusters.
Right, it goes through all the clusters. But if you look at the cluster graph, you look and say, okay, the blue path actually goes through all of them, but I can find another path between the cluster of X and the cluster of Y that only going to another one.
And this would be easy if, for example, you define the cluster graph to be a complete graph.
Right. Right. But here the cluster graph is constructed from a planar graph. So it is a planar graph. So it's not a complete graph.
An edge between two clusters, if there is
An edge
an edge, there is like a
between the vertices and
partition.
correct. Right. So like I said, the reality is a bit messier. So that's why I try to give you the idealized version. That's the ideal we want to get, but actually we don't know how to get this. But this is what we can get, which is much messier, but it still has the same method. But okay, but forget about the reality. Let's talk like we are in an ideal world, and that's what I want. And that's what we are, let's say that we are able to construct this. So I know that I'm lying to you here, but just to get the message across. And we are using the idealized version, and you just think about the graph as a grid like that. It looks nice. And then the C here we call the shortcut partition with hop bound, which is the number of clusters that every shortest path pass through. So we say that the hop bound is constant. And that is what we can construct. So let's assume that we can construct that. Okay, so far so good. Any questions? All right. Now, how does it help? Actually, there is a black box reduction that we can do. We can say that if you can construct this partition with the hop bound, some function epsilon, then you can really construct a tree cover with good additive distortion and size exponential in the hop bound. Now, exponential is not desirable, but it's still constant. Think about epsilon and constant. I still get a constant number of trees. It doesn't depend on the number of vertices of the input graph, even though it's not a good function, but it is something to start with. Again, I won't give you the proof of that. And because we showed that planar graph, you can solve before, we showed that planar graph have a good hop bound, a shortcut partition, a partition with good hop bound, then we can get a tree cover with small number of tree, by small. Then actually, that is a black box reduction, and that's the best we can do with a black box reduction. But if we can reduce to polynomial by messing around with this shortcut partition construction. We'll take, open the black box, do something with it, we can get a better bound, which is the number of tree going to be 1 over epsilon cubic. So this is what we can do by open the black box and do something with it. But if we insist on the black box reduction, the exponential is the best we can do. But regardless of whether polynomial or exponential, what they tell you is that the number of trees is a constant, for constant epsilon. And then, like I said, we had a lemma which saying that we can reduce from additive to multiplicative. So what it means is that we get a multiplicative tree cover with multiplicative distortion 1 plus epsilon with the size is roughly the same size of the additive one that we hear here. So basically, as a result of the conjecture of the people that pose that I mentioned earlier. So it doesn't depend on the number of vertices of the graph. So which was, and one thing that we will come back to it when we talk about embedding. So I probably still have 20 minutes left. That's great. So one property that's not important for now, but going to be important later. I have to lie a little bit here just to make it conceptually simple. In reality, a little bit more involved. But there is a property that we call the root preservation property we get out of the tree cover, which have another property, which is the root preservation property, meaning that when you look at the tree, the preserved distances from x to y, this tree not only preserved distances, but if you look at the distance going through the root, it's still good. Okay, you don't really have to look at the shortest path from x to y in the tree. You just take the path from x to the root, and then from the root to y is still a good approximation of distances that we call the rooted preservation property. It's a kind of strain. Right? Why we care about going through the root will come later. Okay, now it's just a side remark, which is saying if you look at all the vertices, then there would be some trees such that the distance going through the root is a good approximation of the real distance. That's what we're trying to. So, like I said, I'm lying here because it's not a tree. It's not a single tree. It's decomposed into forest, but the detail doesn't matter. At least it's just, in terms of conceptual meshes, a thing about I get a bunch of tree where the distance preserver is going through the root. Okay. Think about it like a few single source shortest path tree. Okay, because single source shortest path tree, like just distance going through the root. But that is another nice property we get out because of this new understanding of structural planar graph, and the proof feel more natural. Even though I'm not sure it's simpler, but
Much simpler.
but it felt to me like more natural proof. Yeah. And so so that's what we get. And now I probably have to tell you what is the tree width. Many of us know what it is, but now it's the time to get to the definition. So far, I just tell you the graph with small tree width is something that look like tree. The figure that I'm drawing. Here's the definition. Now, if you don't understand the definition, that's fine. Okay. So I want to put it out there. There is something that tell you how a graph look like a tree. Okay. So what is a tree width? So I have to talk about tree decomposition. Let's say that I give it the graph. It look like this. Right? It's not a tree. It has a lot of cycle. Right? And then I say that a tree decomposition of this graph is a trees, a back. So what is a back? A back is just a subset of vertices. Okay. So this is just a trees. Subset of vertices. So somehow these back are connected like a tree. And this tree of back has to satisfy three properties. The first two is very natural, like every vertex has to show up in some back. I don't want to leave some vertex out. That's natural. Every edge have both endpoints in some back. Okay, and each back here could contain vertices of the other back. So 4 here contain in maybe 1, 2, 3 other back. So it doesn't have to be a partition of the vertices. Okay, some vertices could belong to multiple back. And I look at every edge. For example, 7 and 8. If I look at the back here, there is a back that contain both 7 and 8. Okay, suppose that I look at 4 and 8. There is a back containing 4 and 8 here. Okay, so if I look at every edge, there has to be some back to contain both endpoints. And the third property is make tree decomposition powerful, which is saying that if you look at all the backs that contain the same vertex, any vertex, look at all the backs that contain the same vertex, it had to indeed a connected subtree. Okay, so for example, if you look at the back contain 5, then 5 containing this back, and this back, they make a connected subtree. Okay, give me another vertex. For example, if I look at 8, for example, 8 is contained in here, then they also make a connected subtree. Okay, so these are the three properties. This is the definition of the tree decomposition. And what would be the width? The width is going to be the maximum backside minus 1. Okay, it's minus 1 for a very strange reason, which is we want the tree decomposition of a tree to have a width 1. So that's why we have to take minus 1. Because, right, so for example, in this tree decomposition, you look at this tree decomposition, the width of this decomposition is 3. Because the maximum backside is 4, which minus 1 will give you 3. Okay, and the tree width of the graph is at most k if it has a tree decomposition of width at most k. Okay, so that is a little bit more formal definition. If you haven't seen this before, it probably look strange. But just to know, so I just want to put it out there so that by the end of the talk you can say, well, what is tree decomposition? I feel like I have to have a slide about it, even though the thing about it is like it looked like tree. That's a simple way to put it. All right, so get back to the shortcut partition, okay, which is we're showing that the idealized version is that I can partition into cluster of small diameter and look at every shortest path it's going through a few clusters. That's the idea. Okay. And let's think about, coming from shortcut partition, how could you sort of construct an embedding? The first thing you could probably do is that, okay, I take each cluster here and I contract it into a single vertex. All right? And see how it's go. And the hop bound telling me that the hop diameter, I should say hop diameter here, of this contracted graph check G is constant, because the shortcut partition saying that for every 2 vertices you can get through by hopping through a few clusters. So you can say that the diameter of this cluster graph is small. And when you have a small diameter, there is a classical lemma saying that when you had a planar graph, this graph is planar, and it has a small diameter, then it has a small tree width. It's not an easy lemma to prove, but this is something is known. So look at the cluster graph, it has small tree width. Now, cluster graph give you some sense of embedding, even though we're not exactly sure. Not exact embedding, for example, this vertex probably not appear in check G, right? So only some vertex appear. For example, if you take for each cluster, you take a single vertex to be a representative. These representative appear, but not the other one. So somehow I had to add the other one. But you can imagine it's a very natural thing to do with a star expansion that we call star expansion. Basically, we'll look at the cluster graph, which two are representative, and then for every vertices in the same cluster, I should attack to the representative by an edge. Okay, so it's just I expand the cluster by a star. Now this expansion doesn't change the tree width. So the tree width of this G bar after the star expansion is the same as the tree width of the check G, because star expansion more like you add more tree to something that already look like tree, and so it shouldn't be different from a tree. So that's the basic intuition. Okay, it's just add a bunch of tree into something that already look like tree. So the tree width of check G is, bar G is good, but not the distortion. Why? Because if you look at X and Y, and here is a path in the graph G bar, which is passing through the center of the cluster, which is the representative here. That's the path in G bar. But if you look at the real path in the input graph, it might not pass through center, but it's passed through some vertex inside the cluster. And if you look at path in G bar, what it said is that, well, actually what you're doing is that you force the path to going through the center. And every time you force the path going through the center, you pay some distortion, which is the diameter of the center, which is epsilon delta. And because the number, so every time you make a detour through the center, you pay the distortion, and actually the path and the number of cluster that you hop through is 1 over epsilon. And if you time with epsilon delta, you get delta. You don't get epsilon delta. So the distortion is too big. And so the next idea is, well, we'll come back to this idea of shortcutting. Let's say that I want to add some more edges here, so that if I look through X and Y, the original path in the cluster graph could go to a lot of cluster. But now after I add some of the edges here, the red edges that I add here, maybe here, look in this picture, then the path from X and Y now going only through a few hops. So go back to the idea of adding more edges to reduce the hop. And every hop here, you pass through, you pay epsilon delta. And in this case, you only hop through 3 clusters. So you only pay 3 times epsilon delta. So that's the idea. Like adding more edges, reduce the hop. But all the same, but you have to be careful because, like I said, adding edges could blow up the tree width, and we want to keep the tree width small. Seem to go back to these problems that we have so far. And that is where the root preservation come into play, which is the last pieces of the puzzle. How do we add the edge? How do I find this red edge to add? Well, we'll look at the tree cover, the root preservation. Again, as that I just remind you the definition. The root preservation tells you that I can construct a tree cover where the shortest path going through the root is good. So a reminder of what the root preservation. And then here's how I would add more edges. Okay, I look at every tree in the tree cover here. Here the graph G bar after star expansion. I look at all these trees here, the only constant number of them. I look at the root here. The roots show up somewhere here in this graph. And then what I do is that I'm going to add every edge from the root to each of these vertices in the tree. Okay? So I add the edges from the root to everybody else. And remember, the number of trees is small. So I actually add only a few number of these vertices. I only have a few roots. And so when I add only a few roots to a tree, the graph, overall graph still look like tree, even though it contains a lot of edges, but it still look like tree because of this thing is small. So basically, the tree width doesn't increase because I only have a few trees. And actually, and then the distortion is good because I know that the distortion going through the root is good by the root preservation property. So that's why I had good distortion, I had good tree width, and that is the end of my talk, I guess. So this is to remind you of the result that we get. Like that, I probably disappoint you because you don't see any serious proof here. It's just very high level and hand wavy. But hopefully, if you're curious enough, then you'll go and read our paper. There's more detail in there. I just hope to get you curious enough to look at our paper. And there's there's a few open problems. The first is that can we construct tree cover with exactly order 1 over epsilon tree? We get cubic, right? I feel like this number is the right thing. We don't have low bound proof, but I feel like it's the right thing, the right number. Embedding with order 1 over epsilon tree width, we get 1 over epsilon to the power 4. And actually, we had a lower bound saying that, omega 1 over epsilon tree width is the best you can do. And so it's nice to match the upper bound with lower bound. Now, maybe it's not that significant to just reduce another dependency in epsilon, but I feel like resolving the problem needs a more understanding of structure of planar graph, and hopefully it gives you more algorithmic ideas. That's what I hope from solving this problem. And for that, I'm stop here. Thank you.
More questions? We had a lot of questions during the talk. I have one question. So what I understood is that the default is that we have that grid representation.
Mm-hmm.
If the distance is too long, we use that route shortcut method, right?
Mm-hmm. Mm-hmm.
How do we decide when to use that? Or when do we decide to add an edge from the root method?
Oh, when you decide, okay. So let me go back one slide. Right, so because previously I talked about the tree cover, like construct a connection of tree, which is totally unrelated. But let's say that I want to add an edge somehow to this graph so that the x and y going only through few hop. This is a bad example because x and y here is already going through few hop. But let's say that you can imagine x here and y somewhere, very far from it. This is the tree cover that we already constructed before in the middle part of the talk. And this tree has the property that, distance going through the root is good. So what I'm doing is that I go through each of these tree, I take the root, and I connect the root to the rest. And so now x and y here have an edge going directly to the root. And the distance from h to r plus r to y is already a good approximation of the distance in the original graph. This is how I decide to add the edges. And because this only have a few trees, so that means I only have a few roots here. Right? Think about it, we have 10 vertices more to add to the graph. And when you add 10 more vertices to a tree, it doesn't blow up the tree width by a lot, because the graph basically still look like a tree modulo just a few vertices. I'm not sure this answers the question, but
It does, yeah. Thank you.
right.
So sorry. So if you're doing this, then you have achieved what you want to achieve for x and y
Right,
already.
for every pair.
Yeah. So where did sorry, I think I'm missing the. I see all the pieces. I believe I understood all the pieces, but I
Right. So the big picture.
Yeah. So, but where does the 1 over epsilon clustering? Where does the small hop clustering come in?
Oh, that's great. So the small hop come in this part, which is saying, like, you take this G and you construct the cluster. You construct the cluster. Okay, so let's see. Right. The hop diameter is 1 over epsilon because of this. But the property that, every vertex, there is a path that passing only through few cluster. So that's telling you that the hop is small, meaning that the hop diameter is small. And there is a classical result, which I didn't improve here. And I should have been focused on that. But the classical is the result saying that if you have the planar graph of small hop diameter, it looks like tree. It has small tree width. Right, so this is where the hop come into play.
Right.
So just to answer the question.
In part. Sorry.
Yeah, but
I think what would help me greatly is if you just at a very high level describe the whole thing.
Right, the whole process is here.
Good.
Start with a graph, construct a shortcut partition.
Yes.
I contract each cluster. Right, here's the contraction. And then now I do star expansion, meaning that for each cluster here, I'm going to attack every vertex to the representative of the cluster by an edge.
Okay.
So I do star expansion, just still has small tree width. And then the next step is I add some more edges.
right? Because if a pass is using too many hops, then
The distortion
it's
is
only
bad.
off by delta.
Right, right.
So you want,
Yeah, so I add more edges so that
if everything's constant hop, then we're good.
Right.
Okay, and then
so that's the whole construction.
okay, so and then these edges are added based on
The-
root
The root preservation property.
Okay. And
Right.
then while adding these edges, you show that the tree width is maintained.
Right, that's correct. Right, so that's its whole.
Thank you.
And then we're also able to add an edge from that root that we have to each of the vertices instead of only the cluster representative.
Yeah, yeah.
The tree cover as well.
That's true. That's true. You can add to all of these vertices, because adding a new vertex to a tree still makes the graph look like tree.
So I guess what I remember from like Arnold's reduction of Steiner point removal to scattering partitions, it all seems like it should be robust to, it's definitely robust to approximate shortest paths.
Yeah.
And probably also robust to this sort of like the fact that you don't care about the number of clusters visited, but just sort of like the
Yeah.
short-
The reduction actually robust.
Is there, do you have to do any extra work to get Steiner point removal from shortcut partitions, or is it basically just
I would say it's not a crazy amount of work,
Okay.
but from my point of view is that it's more like conceptually when you work with approximate path, it doesn't have these property that the subpath of approximate path is an approximate path, right? So that makes it conceptually different, and then we just have to be, let's say, careful about it. Think about it in a more careful way. But if you think about in terms of like, the true technical detail, it's debatable whether we deviate from a lot. But really, Arnold reduction use the exact shortest path, and he have a nice property that every subpath of the exact shortest path is the shortest path. And then in the proof, if everything works out nicely. But when you work with approximate path, it doesn't have this sort of subpath of approximate path is an approximate path. That's not true. And so the proof is you have to sort of work a bit more. But still, the skeleton of the proof is still following Arnold. You just have to work more with the number, with parameter, and then when you replace a path by another path, you have to make sure that the depth of the number of times that you replace is constant, so that it doesn't blow up because of this. We don't have this subpath property. So, good.
Yeah, I guess I would just comment that in the applications of this thing, of these embeddings, the tree width the runtime is exponential in the tree width.
Right.
So getting the tree width down to something reasonable is very significant.
Right. Because
so it would be really great to prove that the order 1 over epsilon.
Right.
That's a very compelling open problem.
Compelling, yeah, I agree. But it's also much low about, so it's a nice
Yeah.
theoretical question as well.
Nice to resolve.
Yeah.
But this is a huge step towards that.
Yeah, it took a long time, but
Yeah.
we're getting closer.
Yeah. All right. Thank you.
Thank you.